So welcome to Empowering Experimental Designs, from simplicity to sophistication. So I'm Dr. Ryan Lekivetz, manager of the Design of Experiments and Reliability Development team at JMP. So it's my pleasure to be here today to talk to you about simplifying your design of experiments journey. And so in JMP 17, with easy design of experiments, or easy DOE. Now, when we talk about designing an experiment, there are some common steps that we take. Right? So the first is the describe, where we identify our responses and factors. Specify, so really which model do we want to fit in this experiment. The design, right? Now we're going to go and create the design based on the factors and the model that we've picked in those first two steps. Now, after we've designed our experiment, we're actually going to collect data. So we're going to run the trials and collect the response measurements. After we've collected them, we're going to fit. So really now we're just going to model our experimental data. And what's our purpose with all of that? So typically it's to predict, right? We're going to be using that model to predict performance, right? Or using that to predict the response. So now let's think about this DOE workflow in JMP. Right? So if you use JMP a lot, we actually split it into two separate phases. Right? So first, we're going to have a DOE platform that's going to create a design in the design phase and use that to create a data table. Right? Now the analysis phase is where we're going to be using that data table to record the data and use one of our analysis tools. Now when you think about a workflow, this really breaks us out of the workflow. Right, and so now we have our data table that really is separated from what we did in the design. So in JMP 17, we've introduced Easy DOE. So this is a tool that will let you stay in the DOE workflow all the way from beginning to end. So Easy DOE guides a user through the DOE workflow, aiding them through the steps with hints. Right, so imagine now you're going through this entire workflow all within one. Now at the same time, so we're calling it Easy DOE, but we offer a flexible mode for those who are further along on their DOE journey. And so once you feel more comfortable, then you'll be able to use more of the features available. Now all of the choices made in the workflow are saved in a new JMP DOE file. And that's going to remember where you left off. And this is going to allow you to share your JMP DOE or your DOE workflow with others or return at any point for yourself. And so really we no longer have that separation, right? We don't have that separation of the design and analysis phase. Now, if we think of that theme of engineering efficiency, there are some pieces I want to highlight in terms of improving efficiency. So Easy DOE is streamlined, right? We now have the entire DOE workflow contained all within the one platform. So while we've combined everything, on the design side, we are still using the custom design and definitive screening designs behind the scenes. And for the analysis, we're going to offer a new interactive analysis tool with model building. And so I'll also say it's efficient, right? So that idea of efficiency, we've made it easy with two different guided modes for both novice and flexible users, right? And so for those that need the extra help, we're going to see there are hints throughout, right? So if we think of a novice user, we're going to be providing them with help anywhere they need it. And really, when I think about the efficiency, it really is quite collaborative. Right? Since DOE is often iterative and collaborative, now you're going to be able to share your workflow with others much easier. Okay, so Easy DOE, before I show it off in JMP, there's just a few points that I want to try to make sure that you take away. Right, so really, we're going to guide users through that entire DOE workflow from design through analysis, right? Not having to separate with a data table and part that off. So the guided mode that I'm going to be showing most of here, so it really is intended to help users that might feel overwhelmed with custom design, right? So you've tried it. How can we, for those who feel overwhelmed the first time they see custom design with too many options, how can we help them? And so as part of that, now we have those hints and additional details throughout to help those users. Now, part of this really is to simplify the choices, right? So simplify the choices and the output while still remaining true to our principles at JMP, right? And so in particular, to really connect the designs to custom design. Now, the new interactive analysis tool, that's going to allow users to easily add and remove terms. So that's one of the things I'm most excited about, is that new interactive analysis tool. And again, just keep in mind, you may see the easy of easy DOE, but we also do offer the flexible mode for those who are more comfortable with DOE. And it still allows them to stay within their workflow and not having to separate that design and analysis phase. So I mentioned that we created Easy DOE to aid novice users, right? So I thought, who would be the best novice user I can think of who really is truly a novice when it comes to experimentation, right? So we enlisted a novice user, my daughter Rory, who was 7 years old at the time, to design and analyze an experiment using Easy DOE. And I'll say, so she has seen some experiments that we've done at home, and we've done some together in the past, but she wasn't the one who was driving everything before. All right, so with Easy DOE, she was the one in complete control over the platform and everything that we were doing. Now, I will admit, so we had talked about some of the concepts that she would see in the Easy DOE. So, I mean, she knew about factors and responses. She had an idea of interactions, which can always be difficult. And she also had a sense as to what we meant by a model. I'd say perhaps most importantly, she was really just excited to try it out. And if you take anything away, that's what I would encourage as well. If you've never tried anything under the DOE platforms before, give Easy DOE a try, and hopefully you'll find it as easy to use as Rory did. So what example did Rory pick? I'll say I suggested to her she could try a paper helicopter. And she said no. She wanted to do paper airplanes, right? And so this she picked on her own, and she decided that she would look at different airplane types. And you see in the picture, those are the two different airplane types she was looking at. Different types of paper. How hard to throw the plane, right? Would you throw it really hard, or would it just be a light throw? And whether or not to use a paper clip. And so her response, so you can imagine as a 7-year-old, what's the most important thing for building a paper airplane? It was the distance flown, right? And the nice thing with that is you can go out and measure that with a measuring tape, right? So we just went outside. It actually turned out to be an extremely hot day, so it wasn't the most fun, but we did it. Okay, so now with that introduction, now let us look at Easy DOE in JMP. Now you will find Easy DOE as the third menu item. So in JMP 17, it's going to be the third menu item under the DOE menu. And so when we click on it, so you can see along the top, we have different tabs here that correspond to the different steps of the DOE workflow. Right? So when a user opens this up, we have that define phase where we're going to input our responses, right, and our factors. Now, if you notice on the guided mode here, there's a lot of additional text that includes giving hints there, right? So for users who aren't sure, and I'll say this happened with Rory, she would look through and she wasn't sure, do I want to maximize, minimize, etc. And she went through and read those hints before deciding, well, if I want to be flying an airplane that she wanted to maximize. So likewise in the factors, when you add factors in EasyDOE, right, you can see here we have continuous, discrete numeric, and categorical factors. And again, as well, for those users who aren't sure exactly what those mean, we also have hints there to show you examples and what that might mean. Now, I will mention here as well, if I were to switch to flexible mode, this looks like the same interface that you would see in custom design. But so let's go back to guided. Now, instead of entering that here, as I said, I'm able to now save in JMP 17 the JMP DOE file. So I actually have here the factors that she had chosen. Right? So I've pre-populated that ahead of time. So we have the type, the paper, throwing force, and paperclip. And I will say it was hard for her to understand the paperclip variable a little bit. The idea of kind of a paperclip factor that meant kind of yes or no, so paperclip or no paperclip. We actually had to spend a little bit of time. But I will say, when I said she was in control, she truly was the one who entered all of these on her own and using the platform the entire time. And she figured out that they were all going to be categorical. The way she had defined those, they were all categorical. And she also had figured out that her response was going to be to maximize, and it was going to be distance. So now, at the top, if you notice, if I want to go switch to my next step, I can click on the tab, the model tab up at the top, as well as at the bottom, we have these navigation control arrows that you can use to switch between them. Now, on the model tab, you'll notice that we have 4 choices here. Again, this goes to the idea of simplifying it for the user. Right? And so we've restricted the users here in EasyDOE, so main effects only. Main effects with some two-factor interactions, which is really like your definitive screening designs. Main effects and all two-factor interactions. And then a response surface model, or that's main effects, two-factor interactions, and quadratics. Now you can imagine this is not an easy tab necessarily for a 7-year-old to think about, which model. When I asked her, it wasn't exactly obvious. But where she got some of her idea for her factors, there was a website that talked about this is how you can try to make your paper airplanes go farther. And it didn't call it interactions, but for instance, it said some paper airplanes will go farther if you put the paper clip on the front. And so that was a natural way to talk to her. That means an interaction when we're talking about modeling. And so she decided that yes, after all of that her model would be the main effects and two-factor interactions. And in fact, and this was where we talked about, so here the user can still change the number of runs if they so choose, but she was comfortable with the default. So the 16, she also recognized that means that she would have to go make 16 paper airplanes and collect data for 16. And she said, you know what, that doesn't sound too bad. And she was the one who made them all. So thankfully I didn't have to do that. Now again, just to mention that idea of flexible mode, if you go to flexible mode, you'll see a similar interface to what you see in custom design again. Right, so again, as you feel more comfortable using EasyDOE, you can now get some additional options in that flexible mode. But so let's say if we're comfortable with our define stage and our model stage. Now I could go back to the define if I wanted to and change that, but instead, let's just go through and make the design. Right, so you notice we've actually separated this into its own step to just show that design before moving on to the collect. And so the idea here is really to have a user take a look at what JMP was suggesting and does this make any sense to them. Right, and so from here, Roy was able to look and say, okay, what this means is that I'm going to be doing a lock bottom. The first plane was going to be lock bottom with regular paper. She's going to throw it lightly and then have a paper clip on the front. And so we talked about that. Was this something that looked reasonable? And she said, great. So now we could move on, right? So we can go to the data entry tab. Now, I will mention at this point at the bottom we have an export data button. All right, so maybe I'm still comfortable working with data tables outside of this. I can click on the export button, and now it's still created the data table that I can now go collect my responses in there. But instead, if I want, at this point, I can just save this jump DOE file and go off and collect the data in this data entry tab. So right now, this data entry tab doesn't have anything in it, right? And so this is where we actually went outside and flew paper airplanes. Now this was where, had I exported the data ahead of time, I could load the response in at this point. All right, so jump is going to be smart enough to match up what was going on there and to load the response. Now instead, so you actually also notice, I'm going to close this easy DOE, and I'm going to load up the data that Rory collected. But you also notice when I was closing this, it said, do I want to actually save the changes to that easy DOE file that I had? And so I'll say no for that as well. So let's take a look. So these are the responses that Rory collected on her paper airplanes. Now I think in the interest of making the text bigger, maybe a little bit hard to see here, but if we look at these factor plots, this actually does show up on the data entry tab. And this is just a main effects plot. To give you a quick idea, so main effect factors, is there something going on just from a quick look at the data? And from here, when Rory looked, she said, well, it looks like the lock bottoms are not quite as good as the darts. All right. And we'll say, well, that's what we're going to go to the analyze to find out. But it's a good, quick way to just look at your data very simply in these single factor plots to see if anything is going on. But let's say if we're comfortable, so now that we've collected that data, now is the big thing. So now we got to move on to the analysis step. And I'll say this was where I was kind of concerned, right? The analysis, when I start talking about modeling and picking terms to a 7-year-old, I was like, I don't know what's going to happen here. So what do we have in easy DOE? So I'm not going to get you to read all this text, but what you'll notice is that we're going to have these different bars. Right, so confidence intervals, they're kind of a representation of the confidence interval, and we're going to have green for terms that are in the model and red for terms that are out. Okay. So if we take a look, by default, JMP has added all the terms into our model. So what I really like about easy DOE though, so let's say I may say, well, this term doesn't seem to be doing anything, centered right around 0. All I need to do is to click, right? I just need to mouse over that and click. And so you notice I can add terms in and out of the model just by a simple mouse click. Right? And so as I do it, you can see here, right? So that root mean square error, or the RMSE, is going to be changing as I add or remove terms. Now, I would say I wouldn't necessarily expect a lot of users to want to do that. So instead, you can also just leave that up to JMP. Right, so at the top of where you get to pick that model, we have a best model button. Right, that is picking a best model according to, in this case, the BIC criterion. But I will say what I had found interesting when Rory had done this, so this model doesn't look terrible. I mean, you might have questions here. They're technically, statistically significant. So I thought this was going to be the hardest tab to try to figure out how to work through it. And so I'll share what Rory had done. She went through and just said, well, I'm going to start taking out everything that looks like it was at 0. So I think hers looked something. And so I said, you know what, to try to figure out what are the most important things that are going on to this paper airplane, this was a pretty reasonable model for a 7-year-old to come up with, to say, well, some of these things are more important than others. Now, I will say, too, that so you may decide, well, you want more flexibility. You may say, I don't like just leaving it up to JMP with that single button. If you move on to flexible mode here, now you have all the options available for generalized regression. Right? And so if you have JMP Pro, it's going to have all of your different options available in the estimation method. But if you have base jump, you'll actually still get a chance to see what generalized regression looks like, right? So even if you do not have Jump Pro, you will still get the solution path to play with in regular jump. So if you go to the flexible mode, you have a different way to go about modeling that data. Now, at any point, though, you can still decide, I don't want to leave this up to easy DOE. Let me go export my data, and I want to do my own analysis. And you can see in here, the data table also has a script for the easy DOE analyze. So that's really saying, what did easy DOE want to do when it was doing its analysis? Well, so this was great, and so I'll say, we'll just go with the best model. And I'll say, you'll see on the next tab, there was a reason for that. But so we could talk about this. So yes, sure enough, it looked like the type of airplane was an important factor. And as well, we had some idea of interactions here, but what does that really mean? Right, and this is what I really like about JUMP is the prediction profiler. Right, so what a great way to talk about interactions than by using something like the prediction profiler. Right, and so now we could see, when we talked about that idea of an interaction, what happens when we change the type of airplane. All right, and so if you look at the paper type, the second plot here, if I change the type of airplane to lock bottom, then suddenly something is going on with that regular paper. I will also share what was interesting. Rory didn't know about how to click on the prediction profiler. Right? The first time she saw it, she said, what do I do with this? And so the nice thing with that, as soon as I was able to tell her once, I said, well, just try clicking on there. Try to move the type of airplane from lock bottom to dart. Then she was able to pick up on exactly what the prediction profiler was doing. And likewise, I'll say for the Analyze tab, I've found that users who have used JUMP for a long time do not expect that the confidence intervals are going to be interactive. Right? So that's something that you kind of have to learn about the EasyDOE platform, is that ability to add and remove terms at any point. Now you'll also notice for the guided mode here, we have this optimize button right at the top. Right? And so similarly, for users who have used JUMP for a long time, they're used to going to the red triangle to optimize, when in fact right above that there's a button right here that just says optimize. Right? And so when I talked to Rory, it was like, well, what if you wanted to make your best paper airplane? What would you do? And so that's really that idea for the optimize button. Now, if you notice, though, there is one extra step. We talked about the 6 steps of the DOE workflow. But at the end here, we also have an additional tab for report. Right? So let's say if you want to share with your colleagues at the end of completing this paper airplane experiment, right, if she wants to tell her friends what she did, we have a final report at the end of EasyDOE. Right? And in this report, it's going to talk about the different factors that were chosen, the response, right? It talks about the different model terms that were in there. And so you can see that this is kind of a summary of everything that was done, through all of the different steps in the DOE workflow. And I'll say this is where it's important to us to hear about, what type of things would you like to see in that final report? If you think about sharing your DOE workflow results with your colleagues, what would you expect to see in there, and how can we enhance this in future versions? Right. And I'll say from this, you can also see, so I can export this currently as a PDF or an RTF if I want to share that elsewhere. But at the same time, now that I'm done, I can share that EasyDOE file with anybody else, and they can see what I've done in all those steps. Right, so I'll say that, this was nice in terms of an EasyDOE, right? This paper airplane was something easy enough that Rory was able to go through kind of her first experiment on her own, all the way from the define to the predict. But when I think about a lot of designed experiments, what happens when you start making them more complex, right? And so within Easy DOE, in the flexible mode, right, and I'll say, so this we do not offer to the easy users or the guided mode, right? But there's this idea of the changes in custom design, right? This is where you might make something hard to change or very hard to change for a split plot design. Right. And so for those of you who have used JMP, if you've ever created a split plot design, so typically JMP is trying to produce the model scripts that go along with it. But so now the question is, well, what happens if you have an experiment that really is quite complicated? And so how would you go about analyzing that? And so for that, I want to thank you for your time, and I'm going to pass you to my colleague, Dr. Elizabeth Claassen.
All right. Thank you, Ryan. As Ryan said, I'm Elizabeth Claassen, and I'm a senior research statistician developer in the statistical development team at JMP. And I have the pleasure of continuing this conversation with you about the more complex designs, such as split plots, that lead to mixed models and generalized linear mixed models. So why are we interested in mixed models? Sometimes there are limitations or restrictions on our ability to perform those experiments. We might be restricted in the number of experimental units that we have available, or as Ryan mentioned, some of those factors may be easier or harder to change between the runs. When we design our experiments with those limitations, the analysis should also account for those restrictions. But JMP makes this more complex analysis, which is sometimes very daunting to a new user, much easier. And while today's focus has been on designed experiments, both with Rory's design and what I will be talking about, mixed models are often used in survey analysis and then with some observational studies, such as when there are hierarchies in the survey plan or there are groups or clusters within that observational data. We can also extend the mixed model to the generalized linear mixed model when our response data is now not normally distributed. So the restrictions that I mentioned before lead to these mixed models. It's the standard for analyzing data when we have more than one source of variation, such as we have a blocking factor or we have a split plot design. Lost my place, excuse me. And so mixed models are the standard, but the linear mixed model, the basic mixed model, assumes that that response is continuous with no bounds. It could run from negative infinity to infinity and at any value in between. But what happens if your response is a discrete count, such as the number of defects on a wafer, 0, 1, 2, 3? Or maybe it's a binary response, such as yes, no, just pass, fail. Or it's a proportion in terms of some y value out of n. So y being the number of parts that passed quality control out of some batch size n. So this is where the generalized linear mixed model comes in. We're going to model these responses in a generalized form. The GLMM is just an extension of the generalized linear model, which you may have heard of, such as logistic regression, when you have a binary or binomial response, Poisson regression. Normal regression is just a special case of the GLM. And then any analysis of variance model when we have a categorical factor as opposed to a continuous factor. Before I get to my example, I like to remind myself that there are two things that a model should do for us when we're working with data. Whether it's a linear model, such as Ryan and I have been talking about today, or the various machine learning models that you can fit in JMP. And the first one, which is less important with the machine learning models, but very important with the linear models, is that we want to plausibly describe the process that gave rise to our data. How do those explanatory factors affect the response? What are the probability distributions, whether it's normal, binomial, Poisson, that are involved? And then the second, which is true for all models, is we want to allow or facilitate addressing that objective that motivated us to go collect that data in the first place. We want to test a hypothesis, estimate a parameter, make a decision. Experiments can be expensive, right? I don't have to tell you. And so if our model doesn't allow us to make the decisions that we want from the data that we collected, that's expensive. And it's a waste of time and it's a waste of money. And so we want to be as efficient as we can. So we want our model to allow us to address those questions. So the example that I have today is based on an experiment that I worked on with a graduate student in the Biological Systems Engineering Department at the University of Nebraska several years ago when I was finishing up my graduate school work. They were trying to develop a new product and had restrictions to their manufacturing process, which resulted in a split plot type design. I can't get into the specific details, of course, but we do know that they had 10 blocks available that could serve as their whole plots. They had a 2x3 factorial design. The factor number 1 was the hard to change factor, which had a low and a high level. They were basically 2 different materials that they were using. Factor 2 was an easier to change factor that had a low, medium, and high level, sort of like the throughput in their machine that they were using. The response that they were measuring was the proportion, y out of n. That was the number that passed their quality control at the end. And the n was the number of parts per batch that were run. In this case, our batch sizes were all the same at 20, but it doesn't have to be a constant batch size. You could have multiple batch sizes in order to, when you're fitting this sort of model. For those of you who are mathematically inclined, because I know there's going to be 1 or 2 of you out there, here's our one equation for the day. That's our model that we're fitting. So we want to model that proportion as a measure of an intercept, our whole plot factor, our whole plot error term, our split plot factor, any interaction that we might have, plus that residual error. And in JMP, we can fit that either with standard least squares or in JMP Pro with mixed model. And one more before I get to the actual demo. This is just an overview of what the ANOVA table will look like for these data that shows our randomization scheme. We had our whole plots and our X1 factors were randomized to those, and our split plot units where our X2s were randomized to those, and we combine them over for that full ANOVA with just our degrees of freedom that we will have. And I want to point out here, this lower right-hand corner with the residual. In a linear mixed model, when we're fitting that normal response, we have that residual variance that we're estimating. But in the binomial and the Poisson distributions, we don't have a second parameter to estimate. There is no residual term. And so sometimes we need to consider this term in terms of this whole plot by X2. If we know which whole plot we're in and which X2 factor we have, we know which unit we were in, and that's where that kind of final measurement error is happening. And so we may need this later, and so I just wanted to point it out here. So here's my data table. I used the custom design, and I don't have time today to go through the whole design process like Ryan did, but I used the custom designer in order to set up the design for this experiment. So we can see that we have our whole plots, our X1 and our X2 factors. And a couple of the nice things about using the custom design, and also with the easy DOE, is I could simulate responses. I don't have the real data from this experiment, so I used the simulation in order to simulate the response, and that's in this Y column here. But originally, we said our response was going to be the number of parts out of the batch size. That was our proportion that we were interested in. And so I simulated our number that passed out of our number of trials at 20. And I also created a column that is that proportion column. This is just y over n. So that's one of the first things that was nice about the custom design, to simulate the responses. And the other, which Ryan also mentioned, is it saves out a script for the model that is appropriate for the design that we set up. So I can just hit this fit mixed button, run the script, and voila, I have my report. It's done. Except, in this case, it's using that Y simulated response, but we were interested in the proportion. So I do need to make a couple of changes. I can do that in a couple of ways. I can either use the column switcher and just switch to that proportion column that I created, or I can go back to the model dialog and change it out there. I'm going to need the model dialog for a couple other things, so I'm going to launch it from there. Make that one go away because I am done. Now I will switch out that Y response for my simulated over trials, that proportion response, and then run that. This is the model I'm interested in. I want to model that proportion as a function of these factors. And we get our report just as quick as that. We start with some plots that tell us sort of a visual clue of how well our data are fitting. On the left, our actual by predicted plot, that's using the fixed effects only from the model to predict our response. And that looks pretty good. And when we look at the conditional plot, that's actually using the estimated effect of those blocks in our predictions. So if we wanted to go and predict specifically for this run that we did, what is our response? I think this looks like a pretty good fit. So I'm going to continue on through my report here to take a look. We have our random effects here as our first section. We can see that we do have some variability due to the whole plots, and then our residual variability. We have the parameter estimates, and then finally the fixed effects tests. And if I look at the fixed effects test, I can see right away it looks like I have a significant interaction, just like Rory found in her experiment. And so I want to explore that further. And so, like Rory did, and like they have in EasyDOE, we'll use the profiler. Pull in the profiler, make that a little bigger for you. And we can see here, click through it. As I click from low to high for that X1 factor, our response trace here on the X2 factor changes quite a bit. You know, when we were in the low, those responses were all fairly high, but when I'm over on the high, we drop down quite a bit. Now, I want parts to pass quality control, right? I don't want to have failures, so I clearly want to have an optimized response. So I want to look at the low, and then over on the X2 factor, it looks like the medium gives me the best response. And here's where modeling proportion data as a continuous response that could take on any value shows up, that we could have problems. If I look over here, I have a predicted response of 0.9, so about 90% of my parts passed, but my confidence interval goes up to 1.08. I can't have more parts pass quality control than I had parts to begin with. Right? I can't have 21 parts pass when I only had started with 20. So this is a problem. I need my proportion to be between 0 and 1. How can we fix this? And this is where the generalized linear model or mixed model comes in. So I'm going to go back to the model dialog, and I'm going to switch now to the generalized linear mixed model, personality. I need to remove my that proportion column that I had, and put in each of the separate columns that are the y value over the n. And this is specified in the same way that like generalized regression or GLM within JMP are specified. We specify both the y and the n to model this binomial response. I've defaulted to binomial. I'm going to leave my model as it was from the original model and go ahead and hit run. Right away, we have a model. And we take a look. What I look at first when I'm fitting a generalized model is at this generalized chi-square degrees of freedom statistic. This is a measure of any over-dispersion that we might have in the data. We have more variability left, basically, than we have accounted for from our model. If this was 1, we would have a very good fit. We've accounted for the variability. But this is almost 2. So there's some other variability that we didn't account for that we should take a look at. And that takes me back to that ANOVA table that we looked at. In the linear model, we have this term down here that was the residual. We don't have a residual in the binomial, but there's clearly some variability between those individual runs that we should account for in this generalized model. And that whole plot by x2 term is how we're going to do that. So one last time to the model dialog, I'm going to go to the random effects and add in that whole plot by x2, that place where that unit of observation occurs in this design. Hit run one last time, and now I have my model. And I can see that this generalized chi-square statistic is now essentially 1. We accounted for that variability in those unit observations. Because we've accounted for it, it means all of the subsequent decisions that we make are going to be more accurate. If we had not accounted for it, we would essentially be saying we're more confident about our responses than we really are. We would have potential for more type 1 error. Our confidence intervals would be too small. But now we've included it, and it's going to make everything essentially better. We'll have better decisions. We look at our variance components. We have some variability to the whole plot and to that term that we just added, that unit level variance. About the same amount of variability between those two. Some people sometimes ask me about this lower confidence interval limit on those variance component terms, because variance, we can't have a negative variance. We don't think it should cross 0. And so maybe this variance really is just 0 because our confidence interval crosses 0, but I don't typically worry about that. First, because we only had 10 blocks, 10 whole plots to begin with, so we don't have a whole lot of data to be very confident about that interval. And we know that we need to include that whole plot term in order to have the correct test statistic for our x1 factor. That whole plot is where the x1 was randomized to, so we need to know about its variability in order to sort of properly test x1. And we knew with the whole plot by x2, we knew from our previous generalized chi-square statistic that we needed to include that. So the fact that this is still slightly negative, I'm, again, not worried about it. So then we can continue on. This defines our model. This is how we design things, so I'm not going to consider that. We have our parameter estimates, and we have our fixed effects tests. And again, just like we saw over when I fit the proportion in the mixed model platform, we can see that we have our significant interaction term. But I want to point out one difference. I mentioned this with the over-dispersion term. If I look at the test just for x2 here, when I didn't include that over-dispersion term, it shows as being highly significant. When I have included that x term, it's now sort of just over our usual significance factor, 0.05. And that's what we can see if we don't account for the over-dispersion. We might make a decision saying that this is important when in fact it might not be. In both cases, our interaction is significant, so we need to focus on the interaction. So again, we can take a look at the profiler. Make it bigger. Come on, there we go. And we see sort of essentially the same sort of plot that we saw. In the low, all of our responses over on X2 are fairly high, but when we switch over to the high, we have that same drop-off, which is what we would expect. We're still modeling the proportion, just modeling it slightly differently. So if I want to maximize, again, I want to have low, and I want the medium. And here's where we have fixed that problem that we saw in the mixed model. Now, my estimated proportion is about 90%, almost 91%, and my confidence interval is from 75 to 96, 97%. So I'm now within the bounds of a proportion. Now, if I want to be sure that my part is going to pass quality control, maybe having this lower confidence bound of 75% isn't high enough. And I'm not sure that maybe that these are statistically significantly different as I look across my X2 factor, the low, medium, and high, those are all pretty close. And so what they did is they took this result and then they went back and sort of focused on what can we do to improve our process when it's clear that the low factor of X1 is where we want to be, but maybe we can refine sort of our X2 to get a better response. So that's sort of where they left off. But I wanted to point out one other part that I think is really fabulous about our GLMM platform here, and that's in the multiple comparisons. So I want to use the interaction term because we decided that we have a significant interaction. And I'm going to use my all pairwise comparisons and take a look at whether or not these are sort of significant here that we saw here in the X2 term. And so we add that, and we initially get, so here's all of those estimates that we saw in the profiler. And when in the estimate column with a GLMM, we're modeling what's known as the logit, the log odds, so the log of the probability divided by 1 minus the probability. So that's what's in the estimate. I don't think in terms of log odds. I don't know about you. I think in terms of probabilities. What is the probability my product is going to pass? So we immediately give you a conversion to that probability. So those probabilities are what was shown in the profiler. We have the standard errors. And then if I want to look at those comparisons, stretch this out. And so I said, okay, where an X1 was low, I know that's where I want to be, but do I have a difference between the X2 factors, say when in the low and the medium level? And so I have my estimate there. And I come over and I have an odds ratio. So when I have the difference in the log odds and I take the exponent of that, I have an odds over an odds. If you're in the pharmaceutical industry, you're used to seeing odds ratios all the time. This is very commonly used. And so in this case, our low factor is about 0.47 times as likely, not particularly helpful, of having having a pass, having your passing the quality control than the medium level. But when we look over, we see that that's not statistically significantly different. If I take a look at the low versus the high, again, in this case, if I'm at the high level, I'm at 1.29 times more likely to have a passing part than if I was in the low level. But again, this is not statistically significantly different. And finally, when I have the medium versus the high, because remember the medium was sort of what we were interested in, I can see that medium is like 2.7 times more likely to give me a passing part, but also not quite significant. So this is why they went back to look at whether or not they can refine that low, medium, high process in X2 while staying in X1. So that wraps up what I have today. There's a whole lot of details that I can't get into. There's math and all of that. So I have created this with some further resources if you're interested in reading more about mixed models. A couple of years ago, myself and Russ Wolfinger and Ruth Hummel, we all work in the JMP division, wrote the Jump for Mixed Models book. There's also the SAS for Mixed Models, which is even bigger, and you can convert some of that information over into JMP. Again, myself and Russ Wolfinger from JMP were part of that team. My advisor, Walt Stroop, wrote what I think is the book for generalized linear mixed models. And then he and I did a statistically speaking webinar for JMP on how do we do mixed models. So I want to thank you all for your time and attention. It's been a pleasure here speaking with you today, and I hope we get to continue this conversation later.